The next thing in this section is area of a surface of revolution. So a surface of revolution is formed when you take some curve, and we're going to call this curve F, and we rotate it about a given line. For example, if we take F and rotate it about the x-axis, we get this figure right here. Well, we know from geometry that the surface area of a cylinder is 2 pi RH. Looking at our surface of revolution here, and if I take just one of these little pieces from inside of here and pull it right out, basically what we have is this cylinder. This portion here is my height, and then this side in here is my 2 pi r, or my circumference. The approximation of each one of the intervals gives us a distinct portion of the solid. Each one of those portions are called frustum, and the area of the frustum is given by circumference, which is 2 pi r times the arc length, because this guy here, how much I move, well, this is just arc length. Well, what that leads to is the following two formulas for the area of a surface of revolution. If you have a function of x that's continuous on some interval from a to b, then the area of the surface of revolution formed by revolving the graph of f about either a horizontal or a vertical axis, doesn't matter which one, is always going to be capital S is equal to 2 pi times the integral from a to b of r of x times the square root of 1 plus f prime of x quantity squared dx, where r of x is the distance between the graph of f and the axis of revolution. So your r of x here is just your radius, and then this guy here looks familiar, doesn't it? That's just your arc length. Similarly, if I give you a function of y that's continuous on some interval from c to d, and I'm revolving this function either about a horizontal or a vertical axis, the surface area is equal to 2 pi times the integral from c to d of r of y, which is just the radius, times the square root of 1 plus g prime of y quantity squared dy, and this was just arc length. And again, r of y is just going to be the distance from the graph of g to the axis of revolution, so this is just that radius. Just like there was only really one formula you had to know for arc length, remember for arc length it was L equals the integral from a to b of the square root of 1 plus derivative squared, and either dx if you're given a function of x, or dy given a function of y. There is only really one formula that you need to know for surface area of revolution, and that is that surface area, the book uses a capital S, but just to make sure that we distinguish it well from the little s that they use for arc length, remember I use the L for that, I write S period A period for surface area, and that's going to be 2 pi times the integral from a to b of radius times the arc length. Remember that arc length is just 1 plus derivative squared, and either dx if you're given a function of x, or dy if you're given a function of y. You don't need to worry about, do I need my radius to be in x? Do I need my radius to be in y? Nope. What you know is that if you're given something that's a function of x, you're integrating with respect to x, all your variables better be in x. If you're given something as a function of y, again, all your variables need to be in y, and you're integrating with respect to y. So let's find the area of the surface generated by revolving the curve on the indicated interval, and this is going to be about the x-axis. The first thing I do is I try to figure out what the radius is, and I don't even try to draw an accurate picture at all of what I have. I just know that I have some function. So here's my function, whatever it is. It's not the right picture, it's actually moved in the wrong direction, but that doesn't matter. And then I know that I'm rotating it about the x-axis. That's important. So my radius is going to be the distance from the curve to the x-axis. If you look at that distance, is that a y movement or is that an x movement? Well, that's y, right? I'm moving up from the x-axis to this point. That's a y. So what that means is that my radius is going to be whatever y is equal to in terms of x. Why? Because this is a function of x right here, and since this is a function of x, I need to integrate with respect to x, so I need everything to be in x's. So y is my radius, but I need it as a function of x. And do we know what y is equal to? Yes, we do. Y is equal to the square root of x plus 1. So in this case, my radius is the square root of x plus 1. After I figure out what my radius is, I do that whole entire part that we did before where we find the derivative, we square it, and then we add 1 to it before I put it in the integral. This is my function. The first thing I'm going to do is rewrite it with the 1/2 power instead of the radical. Then I'm going to take the derivative. Well, the derivative here, y prime, the 1/2 goes and multiplies the front, would be 1/2 times x plus 1, raise it to 1 less, negative 1/2, times the derivative of the inside. Well, the derivative of x plus 1 is just 1. You're just using the chain rule for that. Now I'm going to get rid of the negative exponent and also go back to a radical, and this becomes 1 over 2 square roots of x plus 1. Now we need to square both sides. If I square both sides, I get y prime squared is equal to, well, 1 squared is just 1, and then 2 squared is 4. The square root of x plus 1 squared is just x plus 1. And we're going to go ahead and write that as 1 over 4x plus 4. Now I need to add 1 to it. If I'm adding 1 to it, remember what I need to do is find a common denominator. Well, the common denominator is going to be 4x plus 4. So I end up with y prime squared plus 1 is equal to 1 plus 4x plus 4 over 4x plus 4. Moving over here to the right because we ran out of space, we say that y prime squared plus 1 is equal to, well, that becomes 4x plus 5, and I'm going to go ahead and factor a 4 out of the denominator, 4 times x plus 1. Now let's put it in my surface area formula. My surface area is going to equal 2 pi times the integral from a to b. Well, those limits of integration are given. They're from 0 to 3 of the radius. Well, remember, I found out my radius was just a y movement, and y in this case is equal to the square root of x plus 1. So my radius is just the square root of x plus 1 times the arc length. Well, my arc length was going to be the square root of 4x plus 5 over 4 times x plus 1 dx. Now remember, you can distribute the radical to both numerator and denominator. So this is just the square root of 4x plus 5, and this can be the square root of 4 times the square root of x plus 1. Well, notice now I have a square root of x plus 1 in the numerator and a square root of x plus 1 in the denominator, so those will cancel. And then I have this square root of 4 in the denominator. Well, the square root of 4 is just 2, and when I pull it out, 2 divided by 2 is just going to be 1, so that's just going to be pi. So we have pi times the integral from 0 to 3, and we're going to rewrite that as 4x plus 5 raised to the 1/2 power dx. Using a u sub to solve this, we say that u is equal to 4x plus 5. The derivative du would equal 4 dx. I don't have a 4 dx, so I divide by 4, and 1/4 du is equal to dx. This becomes pi times the integral from x equals 0 to x equals 3 because we didn't change the limits of integration. U to the 1/2, and then times 1/4 du. Moving over to the right because we ran out of space again, the surface area is going to equal pi over 4, and then if I'm integrating u to the 1/2, I get 2/3 u to the 3/2, and this gets evaluated from x equals 0 to x equals 3. Cleaning this up, this becomes pi over 6. Getting out of u's and back into x's, we have 4x plus 5 raised to the 3/2 power, evaluated from 0 to 3. Plugging in those limits of integration, well, 4 times 3 is equal to 12, plus 5 is 17. So we have 17 to the 3 halves. And if I plug in a 0, 4 times 0 is 0, plus 5 is 5, so that's going to be 5 to the 3 halves. Putting that into a calculator and rounding to 2 decimal places, we have pi divided by 6 times 17 to the 3 halves minus 5 to the 3 halves into 2 decimal places, we have 30.85. So our surface area here is approximately 30.85. Our next one, y equals the square root of 9 minus x squared from negative 2 to 2. The first thing we need to do is figure out what the radius is. Remember, we're still revolving this around the x-axis. You don't need to draw a perfect graph for this. We just need some kind of graph, and we're saying, okay, if I revolve this around the x-axis, what kind of movement is that? Well, that's a y movement, but this is a function of x, so I need my radius as a function of x. Well, what is y equal to? Well, y is equal to the square root of 9 minus x squared. Therefore, I know that my radius is equal to the square root of 9 minus x squared. Now that I found my radius, let's find the derivative, square it, and add 1 to it. First thing we're going to do is rewrite it without the radical and write the rational exponent. So we have y equals 9 minus x squared raised to the 1/2 power. Taking the derivative, y prime would equal 1/2 times 9 minus x squared, raise it to 1 less, negative 1/2, times the derivative of the inside, which is negative 2x. Rewriting this without a negative exponent and back as a radical, we'd end up with, well, this 2 and this 2 will cancel, and all we have left is that negative x in the numerator, and in the denominator it would be the square root of 9 minus x squared. Squaring both sides, y prime squared would equal, well, negative x squared is just x squared, and the square root of 9 minus x squared squared is just 9 minus x squared. Y prime squared plus 1 would be x squared over 9 minus x squared plus 1, but we'd need a common denominator, and that common denominator would be 9 minus x squared. Therefore, y prime squared plus 1 would be x squared plus 9 minus x squared all over 9 minus x squared. Well, these x squareds are going to cancel, and we end up with y prime squared plus 1 is just equal to 9 over 9 minus x squared. So now our surface area. Our surface area is going to equal 2 pi times the integral from a to b, in this case from negative 2 to 2 of the radius. Well, that radius, remember, is the square root of 9 minus x squared times the arc length, which is the square root of 9 over 9 minus x squared dx. We are allowed to distribute the radical to both numerator and denominator, so we have the square root of 9 minus x squared times the square root of 9 over the square root of 9 minus x squared. Well, the nice thing is that we have a square root of 9 minus x squared in the numerator and in the denominator, so those are just going to cancel. We have 2 pi times the integral from negative 2 to 2 of the square root of 9, which is 3 dx. Integrating, we have 3x, and this gets evaluated from negative 2 to 2. So this 2 times this 3 is a 6 pi, and if we plug in our 2's here, we're going to have 2 minus a negative 2, or 4. So 6 pi times 4 is 24 pi. Therefore, my surface area here is going to equal 24 pi. Let's look at the last two. The last two have us revolving around the y-axis. The first thing we do is try to figure out the radius. So we have some function and we're revolving it around y. Well, what's this distance over here? Well, the distance I'm moving is an x distance, right? That's an x distance. Well, this is a function of x. X is already an x. Therefore, here my radius is just going to be x. Now what I want to do is find the derivative. Y prime would equal negative 2x. Square it. Y prime squared is going to be positive 4x squared. And then y prime squared plus 1 is 4x squared plus 1. Putting it into our formula, My surface area is going to equal 2 pi times the integral from 0 to 1 of my radius. Well, my radius this time was just x, because remember, this movement right here is just an x movement, and I needed to integrate with respect to x because that's a function of x. X is already an x, so I leave it alone, and that's my radius. And then the square root of the derivative squared plus 1, which is 4x squared plus 1. Well, in order to work this problem out, I'm going to need to do a u sub. So let's first rewrite the radical with its rational exponent. We have 2 pi times the integral from 0 to 1 of x times 4x squared plus 1 raised to the 1/2 dx. If u is equal to the inside, 4x squared plus 1, the derivative there would be 8x dx. Well, I don't have an 8x, all I have is an x dx, so I divide both sides by 8, and 1/8 du is equal to x dx. Therefore, we have 2 pi times the integral from x equals 0 to x equal 1 of, and this just becomes u raised to the 1/2, and then times that 1/8 du. Well, cleaning up over here, this becomes pi over 4, and if I integrate u to the 1/2, I get 2/3 u raised to the 3/2, and this still gets evaluated from x equals 0 to x equal 1. Moving over here to the right, because we ran out of space, our surface area is going to equal, well, if I clean this up, that becomes pi over 6. Get out of u's and go back into x's. We have 4x squared plus 1. That gets raised to the 3/2 power, and this gets evaluated from 0 to 1. Plugging in those limits of integration, if I plug in a 1, 4 times 1 squared is 4, plus 1 is 5. So we're looking at 5 to the 3/2 minus 4 times 0 is 0, plus 1 is 1. 1 to the 3/2 is just 1. Putting that into a calculator and rounding to 2 decimal places, we would have pi divided by 6 times 5 to the 3/2 minus 1. And to 2 decimal places, that would be 5.33. So our surface area there is 5.33. Let's look at our last one, number 7. We're still revolving this around the y-axis, so just like we did before, go ahead and just draw this. We're looking at this, and we're looking at that revolved around the y-axis. The movement from there to there is an x movement, which means my radius is just x, and I keep it as x because I need it as a function of x because I'm given a function of x. Now let's find the derivative. Well, y prime here would be x, and then y prime squared is x squared. Finally, y prime squared plus 1 is x squared plus 1. Plugging that into my surface area formula, surface area is going to equal 2 pi times the integral from 0 to 1 of my radius, and we said our radius is x, times the square root of x squared plus 1 dx. In order to solve this, I'm going to need to do a u sub again. What we need to do is first rewrite it with a rational exponent. Then we're going to let what's being raised to the power equal u. If u is equal to x squared plus 1, the derivative du would equal 2x dx. Well, I don't have a 2x dx, I just have an x dx. Divide both sides by 2, and 1/2 du is equal to x dx. So this is going to equal 2 pi times the integral from x equals 0 to x equal 1 of u raised to the 1/2, and then we have that 1/2 du. Well, here our 2's are going to cancel, and we're just left with pi. If I integrate u to the 1/2, I get 2/3 u to the 3/2, and this gets evaluated from x equals 0 to x equal 1. Moving over to the right because we ran out of space, the surface area is going to equal, well, this becomes 2 pi over 3. And then u is actually x squared plus 1 to the 3/2, and that gets evaluated from 0 to 1. Plugging in the limits of integration, if I plug in a 1, 1 squared plus 1 is 2 to the 3/2. Then plug in a 0, 0 squared plus 1 is 1, and 1 to the 3 halves is just 1. Plugging that into a calculator and rounding to 2 decimal places, 2 pi divided by 3 times 2 to the 3 halves minus 1, and we end up with 3.83. So our surface area is approximately 3.83. That's it for arc length and surfaces of revolution.